All right, so I'm guessing I'll probably do another poll at some point because there's so few people here today, but we'll see kind of moving forward to where if you want to attend in person, we can almost get everybody in here. But for now, just before I forget, at the end of class to mention, next week, group 1, you can kind of meet Monday and Friday. Group 2, you can meet Wednesday. Now, if you want to show up on the other days that aren't your group, if there's empty seats, you can sit there. But kind of priority would be given to people who show up who are in the group that's assigned to that day. Like I said, probably at the end of next week, I'll do another poll just to kind of see if people have reevaluated, if they're going to attend. And if we can get it down to kind of just one group of people who are interested in attending in person, then that's fine. But for right now, even if you show up on, if you're just in the building or whatever, and you think, I want to try to see if there's an empty seat, I would probably suggest based off of today and last class, show up and there might be a seat that you could easily take, okay? That being said, here it is. Does everything sound okay on the Zoom? Last class, it kind of messed up on me halfway through. Nobody wants to let me know?
Yeah, it sounds fine.
Okay, good. All right. Well, last time they couldn't hear me, so I was thinking maybe that was the case as well. So let's go here. We left off last class, I think, right here on this slide. So we'll kind of revisit some stuff we talked about last class and then move on to kind of a new subject or topic. So last class, we talked about these different types of distributions. If I scroll back here, right, we had left and right skewed distributions that we talked about. Okay. We also talked about the mean, the median, and the mode. Right? We ended the class talking about how, if I can get back here, there we go, how the mean is influenced by these extremely high values, right? I kind of gave you these 2 sample data sets and showed you how even if we just changed one number, right, if it was a really high value, it pulled the mean up quite a bit or it increased the mean a lot, but it would just counted as one observation when we were calculating the median, right, crossing off the highest and lowest, and so it largely left the median unimpacted, right? So if we ever had a scenario where there aren't these extremely high values on either side, such that the mean ends up being exactly the same as the median, that would be a scenario that we say we have kind of this normal or symmetric distribution. Right? So when the mean is equal to the median, we have this nice normal symmetric distribution. Once we started to get some extremely high values there on the right-hand side, last class we said that's a right skewed distribution just because it has a long right tail. But the actual reason why we refer to it as a right skewed distribution is because these extremely high values will pull the mean up to the right, or increase the mean, but they won't impact the median, right? That median doesn't get as impacted by extremely high values because they just get crossed off. But with the mean, those values get added into that numerator, right? So anytime we have these extremely high values and the mean is to the right of the median or greater than the median, that's why we were saying we have this right skewed distribution. Now, it's probably a little easier to remember just looking at it. That long right tail means it's going to be right skewed. And what that right skew means is that the mean is going to be to the right of the median, right, or greater than the median, okay? Left skewed is the exact same thing. It's just that we see extremely low values. So these extremely low values decrease our mean quite a bit, but they don't impact the median, right? So now we've got, with this left skewed data, the mean will be to the left of or less than the median. Right? And when that's the case, that's why we say this is a left skewed distribution. Okay? So that's kind of combining what we talked about with the mean and the median and the differences of how they're impacted by these extreme values. And then based off those relationships between the mean and the median, that tells you whether or not the data is left or right skewed. So even if I couldn't see this graph, but I knew that the mean of a data set was less than its median, I would know it's left skewed data. Actually, remind me when we go to Excel later, I can show you an example of this, this idea, because we won't actually be able to see kind of the distributions. Any questions on that? We're just kind of reviewing a little bit and kind of drawing together what we talked about last class. So, sometimes we talked about the median's a little bit more useful because it's not impacted by these extreme values. Now, the mean, the median, the mode we talked about last class were all ways, right, of getting at, I don't know why my floating head's up down here. I thought I meant to minimize that. we know they're all ways of trying to get where's the middle of this data, right? The mean, the median, the mode, we're trying to figure out where's the middle part of this data set at. Right? But now that we know where's the middle part, well, what's the rest of the data set look like, right? Because not every observation is going to be equal to the mean, right? They're going to be, either below or above. So we can think about different ways we can measure what we'll call dispersion or variation in the data, okay? So if we have this commute time data set, the first thing that we could look at is the range. The range is nice because it's quick and easy to calculate, but it's not necessarily always very useful, and I'll show you an example of its downfall, right? So here, if we had the commute times, the range is just the difference between our maximum value and our minimum value. So we look for our maximum, it's 90. We look for the minimum value, it's 20. The range is just subtract the minimum from the maximum, or the difference between these two values, which is 70, okay? Pretty easy. I mean, I'm assuming that you've done things like this maybe in other courses, or at least I don't think this is a wildly new idea, right? Just take the maximum minus the minimum. That gives you the range of that variable, okay? So how can that why isn't that maybe the most useful thing? So let's go, I'm just going to use Excel to kind of show instead of doing this by hand, honestly, because I think I can just type it a little quicker and it gets at the same idea. But I would suggest taking notes, you don't have to do this in Excel, you can just take the notes. So let's say we had a data set. I think what I want is 0, 1, 2, 3, 4, and 100. Let me think if that's what I want. So 7, 10, 110 divided by 6. So it's not what I want. All right, well, this will work. And then over here, I'm going to do 47, 48, 49, 50, 51, 52, 52. Right? Or no, sorry. I'm jumping ahead to the next example. Let's do that. Okay, so 0, 48 through 51, and then 100. Right? And then 0 through 4, and then 100 here. So if I want to find the range of both of these data sets, first of all, if I'm just looking at them, I don't know which one I would say has more variation, right? I mean, here, there's really only one observation that differs from each other. I mean, 0 through 4 are very close to each other, and there's only one observation that's further away. But here, we have two observations because 0 and 100 are going to be pretty far from where the mean is, or where from the majority of the rest of the data is. Okay? So if we look at the range and say, well, look, it looks like this data set has a little more variation, but if I calculate the range and take the maximum minus the minimum, right, I'll get 100. And then over here, if I take the maximum minus the minimum, I'm still getting 100. So here highlights an example where, look, I have two data sets here that are very different, right? But they have the exact same range. I mean, you could imagine, even if I make this data set the one that has more variation. So let's say I go something like this, 20, 40, 60, 80. Well, now I would look at this and say, this has a lot more variation than this data set, but the ranges can't tell me that, right? The ranges are only kind of operating off the minimum and the maximum values. So we're going to need to go one step further, right? We're going to need to come up with a different statistic that tells us more and captures the variation from every single observation in this data set, right? Because right now with the range, we're only using the maximum and the minimum, right? It's not giving me a lot of information. So we're going to come up with this measure for the variance, right? So what the variance is going to do, and I said this last class, it's not theoretically probably the best way to think about it, but I think intuitively it kind of hammers home what the variance is going to do. It's going to capture the average deviation from the mean, or the average how far away each observation is from the mean. Right? So we're going to capture, on average, how far away is each observation from the mean. That's a good way to think about the variance. Right? So we're going to notate the variance for the population with sigma squared, right? We said we use Greek letters, kind of like with the mean, we use mu. Here, excuse me, we're using sigma squared to represent our population variance. And we'll go down in a second. Our sample variance is going to be S squared, but I just want to focus on just having this on the screen for now. So how we're going to calculate this population variance is we first need our mean. Right? Well, we know how to calculate means now, so that's good, right? We'll have that mean calculated. We'll then go through, starting with the very first observation, and whatever variable we're looking at, we'll take the first observation's value and subtract the mean. Once we do that, we'll square that difference. We then go to the next observation. We take its value for the x variable, subtract the mean, square that value. We do that for every single observation and then add them all up. Now, one thing that we'll start referencing to this as, instead of saying the difference, I'll usually say the observation's deviation from the mean, right? But really that's just a fancy word of saying the difference between the observation and the mean squared. Okay? So once we add all these up, we then divide by the total number of observations. And we'll return to this formula a couple times and I'll explain a little bit more about what's going on. But first I just want to get down kind of how we compute this, right? What steps we would actually take. So the sample variance is going to be the exact same thing, right? Go through every observation. Instead of subtracting the population variance now though, we don't have population data, we just have sample data, so we would subtract the sample mean. Once we have that difference, square it, do that for every single observation, add them all up. The only difference with the sample variance is instead of dividing by the number of observations we have, so before with the population variance, capital N was the total number of observations in our population data set. Lowercase n is the number of observations in our sample data set. So instead of dividing by the number of observations that we see in our data, we'll divide by the number of observations minus 1 for our sample variance. So we'll dive a little bit more into why that's the case once we get to some things like hypothesis testing and confidence intervals. But essentially, this is going to help us err on the side of caution, right? The idea that our sample may not be capturing the population perfectly. And so if I divide by a smaller number, what's that actually going to do to my variance? If I've got this numerator and I divide by n minus 1, so let's say I divide something by 1 instead of 2. Right? So if I had the number 10 and I divide it by 2, that's 2 maybe is my observations. 10 divided by 2 is 5. Well, what happens if I divide it by n minus 1? So 2 minus 1 is 1. So 10 over 1 would be 10, right? So if I divide by a smaller value, it's going to increase that sample variance, right? Because I'm only dividing by n minus 1 instead of n here. And that'll help, with a higher variance that errs on the side of caution once we get to some statements that we'll make with hypothesis testing. Okay? So that's a little bit of a look into the future there, but there is going to be a difference between the population and sample variance here. Okay? And the only difference is that you divide by n minus 1 instead of n. Also, this isn't overly important, but anytime we would look at the variance, the units will be whatever the variable was, right? So if it was income, we would say the units of the variance is dollars, right? If it's height, right, then the inches are, or the units are going to be inches, right? It's whatever the variable is that we're looking at, that's the units of the variance as well. So here we'll kind of have in words what I just described with that formula. So the first step, we have to have the mean, right? We're going to be looking for the deviations of each observation from that mean, so we need to start out with having the mean. We'll then subtract the mean from every observation. Once we do that, we'll square each one of those differences or each one of those deviations. Once we've squared every single deviation, we'll add them all up and divide by the total number of observations we have. If it's population data, if it's only sample data, we would divide by n minus 1, right? The number of observations minus 1. Like I said, to understand exactly why for right now, why we're doing that, it won't be clear until we get to hypothesis testing. But for now, it's just basically we're just going to have to kind of memorize or remember this. Okay? Any questions so far before I keep moving? We'll go through an example with some actual values here in a second. Okay? So before we go through an example, I also want to mention that we're not just going to look at the variance. We also have one more measure of dispersion, which is the standard deviation. Now, these formulas might look a little familiar because they're the exact same thing we have here. So sigma squared and s squared for our population and sample variance. But for our population and sample standard deviation, it's the same thing. We add one more step, which is just take the square root. All right? So once you have the variance, if you take the square root of the variance, that's your standard deviation. Right? So if I had a variance of 100, right, I use this formula to calculate it. I then take the square root of that, or take the square root of my variance of 100, I'd be left with a standard deviation of 10. Right? Square root of 100 is 10. So the reason why you might say, well, why that? We're just inventing statistics, right? We're just scaling the variance here, right? We're just taking the square root. We haven't actually done anything meaningful. I could come up with my own statistic where I'm like, I don't know, cubing the variance and then taking the 8th root, or something goofy. Well, the reason why is because once we get to some other formulas that we're going to use in this class, once again with confidence intervals and hypothesis testing, the standard deviation has a better interpretation, kind of like it's easier to verbally discuss what the things like what would I want to talk about? Once we get to confidence intervals, it's easier to think about what a certain percent of the data will lie, and the standard deviation will tell us certain things about what percent is to within a certain amount of the mean, and so it's a lot easier. They're a lot more functional once we get to some other topics. But for now, just know that the standard deviation is simply the square root of the variance. Okay. So let's actually sit down and calculate a variance, or at least walk through the steps, right? So I have this old, I think 2010 or 2012 football salaries for Ball State coaches that was in the paper here. So I wrote them down. I've got 10 coaches here, everyone from the head football coach to the video tech guy. But this is a nice data set because I really can think about this as like a branch within a company or something where you've got, I don't know, the CEO or the manager, you've got the positions underneath them, maybe even like a low paid intern here as the video tech guy. So we've got kind of this data set, which we can kind of think about. We would see something similar from any company, right? Any division of a certain company. So maybe not quite this high a salary, but so we've got the different salary amounts, right? And we can see that, the majority of them are in this $75,000 to $150,000 range, but we've got kind of two outliers, right? One relatively high and one relatively low, okay? So how would we calculate the variance? Well, the very first thing we need is what? We said part of the process is we're taking the deviation from the mean. So in order to do that, I first need to calculate the mean, right? I can't do much without the mean here. Oops. So how would I calculate the mean? I just add all these values up and divide by the number of observations, right? So I'd add these up and divide by, I think I have 10 coaches here, okay? So that's kind of what we did last class. That shouldn't be too bad, right? That's giving me the average or the mean salary of these 10 coaches. Okay? What we're then going to do is go try to calculate the population variance. Well, if I now have the mean, what I'm going to do is take that first observation, subtract that mean of 134.5 thousand, square it, add to it 150 minus that mean of 134.5, square that deviation, then add to that 124 minus 134 squared, so on and so forth until I've gotten every single head football coach, right? Once I've done that, right, so that's essentially what's in these square brackets. I went through every observation, subtracted the mean, and then squared that deviation, and then added them all up, okay? I then would divide by the total number of observations. But another way I could write that, and we'll kind of see this in some different forms, so I wanted to introduce it. Instead of like having this huge long numerator and then putting like a line that was divided by 10, to make it look a little bit cleaner, I just put multiply by 1 over 10. So anytime we divide by a certain number, it's the same as multiplying by 1 over that number, right? You can almost just think about we would just still need to distribute that 10, right? So we might see this written two ways, but really all we're doing there when we multiply by 1 over 10 is we're really dividing by the total number of observations, okay? But I just want to make you aware that we could also kind of rewrite it as this. Once we get to some later formulas, we'll see sometimes they're kind of have, instead of dividing by something, we just pull it out and multiply by 1 over that. Okay? Now, if I'm trying to enter this into a calculator, it's very, very possible I hit the wrong number, I forget a squared, I forget a parenthesis. It's a lot easier to make mistakes if I'm entering this all in on one line of my calculator. So another process which I would kind of recommend doing, if we're doing this by hand, preventing us from making kind of easy mistakes, is, and also you'll be tested kind of on this. So let's say I've got this data set, right? I had that mean of 134.5 thousand, I think 134.5. I could, right next to this column, for every single observation, go 489, subtract 134.5, square it, write that number down. Then take 150 minus 134.5, square it, write that number down. I could do that for every single observation. So I'm kind of like doing each observation independently. Then once I've done that, I can add them all up, right? That would represent the numerator of my variance, right? I've squared every single deviation from the mean for every observation. I then added them all up, okay? Once I've done that, I only have one more step, right? That's my numerator, and my denominator is simply dividing by the number of observations that we had, 10, right? And that would give me my variance. So this way, you're kind of breaking it down like observation by observation. It's going to allow us to look at some things about the variance here in just a second that we couldn't if we kind of did it all on one line and just hit enter. But, you know, also this is a way, I think, to prevent yourself from kind of forgetting parentheses or forgetting to square one of the deviations and things like that. Okay? But you could do it either way, right? Break it down like this or do it all on one line, right? It's the same process, or it's the same, it'll lead you to the same answer, just kind of breaking down the process a little bit differently. Okay, any questions on that before we keep going? We're okay with this? So one thing we want to think about with the variance, we want to try to understand it a little bit better. So we've got the computation, I think we went through that, but what's really going on? What is it really measuring, right? So if you notice, right, if we had a mean of 134,000 here, I said one way we can think about the variance is it's like the average distance away from the mean that a certain observation is. That's not a perfect interpretation, but that's a good way to think about it. So what we've really done here is for every observation, it's going to add something to that numerator in your variance. So it's going to change, right, the numerator. It's going to change your variance. How much it changes it by is how far away from the mean that observation is. So notice, when I've got observations like of 150 and 124, those aren't as far away from the mean, right? They're pretty close to 134.5. So they don't add near as much to the variance as an observation that's very far from the mean, right? An observation that's very far away from the mean adds a very large amount to that variance. So why would it do that? So if we think about here, any observation, if it's above the mean, that'd be a positive difference. And when you square it, it's a positive. Any observation below the mean would be a negative value, but when we square it, a negative times a negative is a positive, right? We don't care about whether or not it's above or below the mean. We just care that it varies from the mean, right, in either direction. So when we square that, we're treating any variation the same, whether or not it's above or below. What we're also doing is really over penalizing a variable. I should say penalize, but I don't know, it's okay to use that, but we'll over penalize a variable if it has an observation that's very far away from the mean. So why does that square kind of over penalize? Well, you can think about it. If I have a deviation from the mean of 1, 1 squared is just 1. So only 1 would get added to the numerator. If I'm 2 away from the mean, 2 squared is 4. I add 4 to that numerator. If I'm 10 away from the mean, 10 squared is 100. So 100 gets added. So as I get further from the mean, when I square it, it's like making that number increasingly larger that gets added into the numerator. So observations very far from that mean, 489 is pretty far away from 134. Notice it adds a huge number to that numerator of the variance, okay? And that's because each observation is adding to the variance. Let me say it differently. Each observation is going to be its own evidence about how much the data set varies from the mean, right? Now, the observations that don't vary much from the mean won't add a lot to the numerator. But observations that are very far from the mean, well, that's strong evidence that in this data set, there's observations that are very far away. And then by dividing by n, we kind of are looking at the average variation that exists. That's why I said we can think about it that way. Okay? I mean, notice here, this one observation, once I add up all these deviations squared, I got 147,000. This one observation accounted for 125,000 of that, right? So most of the variance is kind of being driven by the fact that we have this really extreme outlier, right? And because when we're squaring those deviations, we're kind of over penalizing for that, okay? Any other questions before we keep moving on this? We'll go through another example here, but so we're gonna skip these couple slides here. Probably pick up on Monday with them. Don't get too scared by them. I'm never gonna expect you kind of to reproduce those mathematical proofs. So a possible question we could think about is something like this. So we go back to that commute time data set, right? 7 employees, 7 different commute times. We had the mean for that data set was 45. Right? So we'll talk about how we compute it here in just a second. But another thing, after we've talked a little bit more about what's going on with the variance, is which of these could not be the variance? Which can you rule out right away? Any guesses? Right, a good guess would be A, right? 0 seems like it's kind of different than the other values. But what would have to be true about a data set for 0 to be the variance? Every number would have to be the same, right? Remember, we're trying to measure the variation in a data set. So if we're saying there's 0 variation, what would that mean? It means that every number would have to be exactly the same. So a whole data set of 50s, a whole data set of 3s, you know, whatever number. Now the reason why that would be is because if we think about what's going on in that numerator, well, here, I'll go to a different form of the equation. If I can get there, geez. Okay. It would have to be, in order to be 0, every observation's deviation from the mean squared would have to be 0. Because we can't have any negative values in this numerator. So anytime we would have a positive, we could never like balance it out with a negative. So it would have to be that every observation was adding 0, which means every observation would have to be equal to the mean or all the same number. Okay? So that's kind of just a good thought experiment. And one thing that'll be really easy to do, like if I ever give you an example, if it looked like this, we also can rule out negative values, right? We know that they can't be negative. Has to be 0 at the very least or higher. And why you would be doing anything with a data set that had a variance of 0, like, you know, it's all the same. Like, what more can we really, you know, it wouldn't be that interesting. If we actually go through and compute this variance, we'll take that mean of 45, we'll subtract it from that first observation. So 20 minus 45 is negative 25, square it, write that number down. 35 minus 45 is negative 10, square that, write that number down. Do that for every single observation, then add up all those deviations squared, we get 2,900. And the last step to kind of give us this average variation from the mean, we divide by the number of observations we have, which was 7, okay? Once again, we can see, you know, evidence that if we think about the value of 45, right, this observation was 45, well, the mean's 45, so it absolutely adds nothing to that numerator because it's not varied from the mean at all. Now, when we get values that are a little bit further away from the mean, right, they add in kind of smaller amounts. And then the values that were very far away from that mean of 45 added significantly larger amounts to that numerator, okay? Any questions on this before we keep moving? We're okay with this? Where are we at in time? Oh, we're perfect. All right. So this is unlikely to happen in practice. This is kind of like a hypothetical for me to prove a point. Usually you know if you have population or sample data, and if you have population data, you compute the population variance. If you have sample data, you compute the sample variance, right? But let's say I had that data set that we just used, and someone comes to me and goes, I tell them, I thought that was every employee. And they go, no, that was just like one branch or one division. I go, oh, so I just had a sample of a much larger population. They're like, yeah. So I'm like, oh, calculated the population variance, so I have to recalculate this, right? But if I have the same data set, remember, the process to find the sample variance is exactly the same. It's just the very last step we divide by n minus 1, or the number of observations minus 1, okay? So if I go back to what I had done before, the only thing that's going to change on the screen is what? Right? Instead of divide by 7, I'll divide by 6, right? N minus 1. because the data hasn't changed, and the process when I go through the deviation from the mean squared, nothing's going to change there, going from a population to a sample variance. The only thing that changes is that very last step, right? So I would then be taking 2,900 and dividing it by 6. Right? So if I divide by a smaller number, what's going to happen to my variance? Instead of 414, it's going to be higher or lower than that. If I divide by 6 instead of 7, should actually go up. So when I look at these possible answers, I know the only one that makes sense is that 483. Now I can go through the actual process. Basically, it repeats exactly what we did before. When I add up all those deviations squared, I get the same number. It's just now I divide by 6 instead of 7. Okay? And like I said, in practice, that's not the case. I just want to use this to highlight that because we're dividing by n-1, we end up with a slightly higher variance. Okay? Erring kind of on the side of caution, and not thinking that there's less variance than there could be in the population data set. Okay. Any questions on that before we keep going? Okay, so let me not go there yet. Let's go back to these two data sets that we had. Okay. I think I want to change these a little bit. So let's go 1, 2, 3, 4, 5, and 100. Oh, actually, sorry. 0, 1, 2, 3, 4, and 100. And then this one, let's look at this one. Let's go 0, 20, 40, 60, 80, and 100. Right? So we still have two data sets with the same range. Right? So we might want a, if we look at this one, initially we think, looks like there's more variation kind of in this data set. Right? The numbers are kind of all over the place as opposed to here, most of the numbers are near each other, but only one's far away. But here's where sometimes our eyes can kind of trick us, and we actually look at a statistic that tells us about the variation in the data set. We might come up with something different. And I'm sorry, I don't know why I typed that var.s in already. Let's try to calculate the variance. So the function that we're going to use to calculate the variance is var.s. Right? Sometimes when I'm in Excel, I think in Excel functions. So var.s is going to find the sample variance from the numbers that we select. So we're going to find the sample variance of this little sample data set that I came up with, right? So the only difference between the population and sample variance in Excel is instead of var.s, if I want the population variance, I use var.p, right? That's the only difference, right? So var.s gives us our sample variance. If this was a population data set, we'd use var.p, okay? So var.s, we've selected the variable here. We'll hit enter. We get a variance, right? Calculates everything behind the scenes for us. It calculates the mean. It looks for the deviation from that mean for each observation and squares it. It adds them all up. And then for the sample variance, var.s, it divides by n-1. Okay? Now, if I do the sample variance for my other data set here, so var.s, I select these observations. We said just by looking at it, we might think it has a higher variance, right? Because these numbers are kind of varied a little bit more. But remember, I said a better way to think about, a good way to think about this variance is the average deviation from the mean, okay? So if we hit enter there, we actually find that the variance is lower for this data set. So let's think about why. So I'm going to right click and just insert a cell. You don't, like I said, you could be doing all this. You can be doing some of this by hand if you wanted to. But I just want to use it to kind of highlight the point. So I think we went over this last class with the functions in Excel for measures of central tendency. So the one that we used to find the mean was simply this average formula, right? Or function. So equals average, you then select the range of data, right? We said we could do the median and the mode as well, right? The only thing there would be equals median, select the data that you want to find the median for. Equals mode, select the data you want to find the mode for. Right? Pretty easy. So let's find the mean using that average function. I wish that Excel named it the mean function, but I don't know. I don't know why they didn't. So we'll find the mean of this other data set. Now notice, if the variance is the average kind of deviation from that mean, in this data set, the mean was 18. you know, even these values, even though they're close to each other, they're all like kind of far away from that value of 18. And then the real thing that kills us here is 100 is very far away from 18. So when we square that deviation, it's going to add a lot to our variance. Okay. Now over here, we have a mean of 50. Well, now those extreme values of 100 and 0, even though they're both like 50 away, 50 isn't near as far away, you know, as what? Almost 80. 100 is almost 80 away from the mean over here. So yeah, there are going to be some observations. They all add a little bit more to that variance, but we don't have like one observation that's going to add a ton to that numerator in the variance. So, you know, it's a little bit, you know, we typically think of the variance as giving us a measure of the variation in the data, and it does, but truly what it's capturing is kind of the average deviation from the mean in that data set. Okay? And now here's where we can relate to something that I believe that we went through last class. I kind of did some different data sets of different sizes and kind of showed that, yes, the mean is greatly influenced by extreme values, but it doesn't pull the mean up to the right or kind of increase the mean near as much if we have more observations, right? Because when we have more observations, any one observation doesn't carry as much weight, right? Being 1 out of 100, I carry less weight than 1 out of 2, right? Same kind of thing applies to the variance. Extreme outliers like 100 here influence the variance a little bit more than if we had like a data set with 1,000 observations that were all between 0 and 4, but only one of those observations was 100. So, you know, when we think about higher data sets with a higher number of observations, these outliers won't influence the variance near as much, okay? But here, we can kind of see they can quite a bit, right? And sometimes the direction of these variances for different data sets might be somewhat counterintuitive when you're just looking at the data, okay? All right, so I wanted to show you that. I'll show you one more thing in Excel real quick. Here's kind of a summary of, you know, the average, the median, and the mode. Those are named pretty easily. The variance, var.p for the population, var.s for the sample variance. The other equation that we have is this standard deviation. Now we can do .p for the population standard deviation or .s for the sample. Right? It's as simple as, so we'll call this SD, right? So equals STDEV .s, so this would be the sample standard deviation. If I did .p, that was what I would use if I had a population data set. So I'll kind of select my cells there. STDEV.s should do all the computation. Same thing as var.s did, but at the very end, it's going to take the square root as well, right? So I hit enter, get my standard deviation. Now, I want to show you another way to find that standard deviation. If I already have the variance, what's another way I could find the standard deviation? I said earlier, the standard deviation is simply the square root, right? So how do I do the square root in Excel? It's actually this function called SQRT, square root, right? SQRT. So the square root, SQRT, select whatever number you want to take the square root of, which was the variance there. And sure enough, we get the exact same thing, right? So 2 ways of doing it. I usually just use the square root if I've already got the variance. I don't know why, but you can use stdev.s as well, okay? Any questions over that? Okay, so let's do one more thing. And you kind of have this here in the slides, but I'm gonna use this dot cam today. Let's see how this this goes. I'll probably at some point add a question onto an online quiz about which one you like more, kind of me being up here on the board. Today it wouldn't be as bad because you're all kind of here on this side, but using this board space and having people kind of back here, and I don't know, it's kind of awkward. So let's see how we like this. I use it for some of my other classes. It gets a little bit clunky the first time I have to turn it on with kind of Zoom here, but once we get it going, it should be all right. All right, and if this light helps, we'll see if the light helps. Kind of get to 0 in here. Sometimes it has to focus on like one object. It's fairly clear, I think. Okay, so we'll go here to make sure it's straight. Okay. So let's say I've got 2 different distributions. First, we'll kind of do something that looks something like this. We'll say this first distribution has a variance of, I don't know, 10. Okay? And let's say, I don't know, it has a mean of 50, right? So it's centered around this mean. So we have a nice normal distribution here. Well, let's say I have another variable that has the exact same mean. So its mean is 50, right? But it has a variance of 100. So let's say the second distribution I'm going to draw has a variance of 100. Right? What would this second distribution look like compared to the first? Well, remember, the variance is going to tell us is some measure of how much the data varies from the mean. So one thing we don't want to forget is what's on this kind of y-axis. We usually don't draw it, but really, right, that was the frequencies. Right? I'll shorthand it with freak, I guess freak as I said, F-R-E-Q, right, frequency. So this is telling me that there is a higher number of values near the mean in the data set and a lower number of values further from the mean. Right? So if I now have a variance that's higher, what that's telling me is there's more variation in the data, or the average distance from the mean is higher, right? So it's more likely I'm going to see values that are further away from the mean, right, when I have a higher variance. So these values that are further from the mean for my new distribution should be more likely for me to see, right? They should have higher frequencies. The values over here that are further from the mean, more likely for me to see now relative to before. What that's also going to mean is it's less likely I see values near the mean, right? So it's a lower frequency for those values right around the mean. You know, and if we kind of connect these two, well, I didn't do a perfect job there, but you kind of get what here, I'll get it straight. You kind of imagine what I was trying to do there. So with this higher variance, what we've seen is that values further from the mean are more likely, values around the mean are going to be less likely. So we get kind of this flatter distribution, right? So a higher variance is going to flatten our distributions. Whereas lower variances, what that's saying is, well, the values further from the mean, they're not very likely, right? They're not happening very often. But values near the mean are more likely or have a higher frequency of occurring, right? Any questions on that? I think kind of talking through that, hopefully it kind of helps get at the idea of why a higher variance kind of flattens out my curve. And then a lower variance would kind of peak my curve there. The other thing I wanted to kind of go through is think about, so we can think about how the variance is going to change our distribution. What if I had two variables with the exact same variance? Let's say the first one has a mean of 20. I don't know, let's do our variance of 10 again. Okay? What if I had a different variable that has the exact same variance, but the mean is 40? What's that going to do to our distribution? Well, if we're thinking about here, we're just plotting this variable x. It's going to be the exact same height. Hopefully I drew it the exact same height. I tried to. But the mean, if it's higher, it's just going to shift that distribution to the right. Right? So, you know, we could say this has the exact same variance, but a higher mean. Right? So same mean, but higher variance flattens our curve. Same variance, but a higher mean is going to shift that curve, right? So we can kind of think about, when we're thinking about distributions, those are some things that we might be comparing across two different variables or data sets, and that's how it's going to kind of, I don't want to say manipulate, but kind of alter our distribution. Okay? And let's see, I think he's going to have to hit this button if we use that. So we'll see if we get the screen back. Screen back up here in just a second in class. There we go. So that's what that last slide was kind of getting at. It was saying, look, if we had not just two, but several different standard deviations, standard deviation or variance, still doesn't matter, right? They're really the same thing, just scaled. If they all have the same mean, the standard deviations that are lower are going to be more peaked, and the standard deviations or the variances that are higher are going to kind of flatten out those curves. Okay? And then we talked about how a different mean would shift them. You've got kind of a summary of those Excel equations. I don't think I'll get the Excel assignment up today. It might get posted over the weekend at some point. If not, for sure, I'll post that first Excel assignment on Monday, okay? But I'm also, instead of an online quiz today, I'm going to post the very first Connect assignment as well, right? So you'll still have about 2 weeks to turn that in. So due date will be like two weeks from today. We probably haven't covered all the material for the last few questions. I think there's 13 or 14 questions. You can probably work your way through, I'm guessing, I can't remember the exact number, but about 9 or 10 of them. We've already covered the material, so you can start get a head start on that because you will have an Excel assignment that's going to be assigned on Monday as well, okay? Any questions for me before we get out of here? Yeah. So it'd be I won't know the date off the top of my head. So it's 2 weeks from today. So like 2 Fridays ahead of us. Yep, yeah. So kind of all next week to work on it, and then we'll be finishing up the material that you'll need to finish it. So, you know, if you start working on it now and kind of keep up to date to it, you might be able to have it done by the end of next week, but I'll give you like another week to kind of work on that as well. Okay. Any other questions for me? All right. I'll see, like I said, group 1 will be kind of Monday, Friday next week, group 2 Wednesday. But like I said, if you want to stop by, if you're in the building, there's probably going to be empty seats if you want to kind of join either one of those sessions, okay? All right. Have a good weekend. Stay safe.